On December 2004, at 21 hours 30 minutes and 26 seconds Universal Time, something 50,000 light-years away fired a pulse of energy in our direction. It traveled across half the galaxy at the speed of light. It took 50,000 years to get here. And when it arrived, it hit Earth's atmosphere like nothing ever recorded in the history of astronomy. In a fifth of a second, this single pulse released more energy than our sun will radiate in 250,000 years. It was so powerful that it ionized the upper atmosphere on the night side of Earth, the side facing away from the sun, the side that is supposed to be shielded. It physically altered our planet from 50,000 light-years away. Gamma-ray detectors on spacecraft saturated instantly, their instruments simply unable to cope with what was hitting them. Researchers described it later as so far beyond any previously detected event of its kind that it was essentially off every chart ever made. And the object that produced it was not a galaxy collision. It was not a supernova. It was not a quasar blasting jets of plasma across millions of light-years. It was a dead star, roughly 20 kilometers wide. A ball of compressed matter smaller than a mid-sized city. And it had merely hiccuped. That object is called a magnetar. And it is, by every physical measure we have, the most dangerous category of object in the observable universe. Not the largest, not the most massive, not the oldest, but the most dangerous, in the specific sense that nothing else in existence concentrates destructive potential so intensely into something so incomprehensibly small. And for a long time, we barely knew they existed. Even now, with the handful we have managed to identify and study, they continue to violate expectations in ways that keep physicists up at night, staring at data that refuses to make complete sense. To understand what a magnetar is, you have to start with what it came from. When a massive star, something between about 10 and 30 times the mass of our Sun, exhausts its nuclear fuel and collapses, the core is crushed down into a neutron star. We covered neutron stars in this series before. City-sized, incomprehensibly dense, rotating at extraordinary speeds, already among the most extreme objects in the known universe. But occasionally, under conditions that are still not fully understood, something different happens during that collapse. The collapsing core spins faster. The convective motions inside the proto-neutron star are more violent, and through a process called a dynamo mechanism, similar in principle to but almost incomprehensible in scale compared to the process that generates Earth's magnetic field, the neutron star amplifies its magnetic field to levels that exist nowhere else in the universe. A typical neutron star already has a magnetic field roughly 1 trillion times stronger than Earth's. That sentence should stop you cold. 1 trillion times stronger. Strong enough that if you placed a neutron star where the moon is, it would erase every credit card, every hard drive, every magnetically stored piece of information on Earth, instantly, from 400,000 kilometers away. And yet that field is ordinary, expected, catalogued and accounted for. A magnetar's magnetic field is 1,000 times stronger than that again. We are talking about fields in the range of 10 to the power of 15 Gauss, a quadrillion Gauss. The strongest sustained magnetic field ever created in a laboratory on Earth peaks at around 45 Tesla, which is 450,000 Gauss. A magnetar's field is roughly 2 billion times stronger than the best we have ever managed. It is a number so far beyond human engineering that it barely registers as the same category of physical phenomenon. And that field does things to the fabric of space itself. One of the predictions of quantum electrodynamics, the quantum theory of light and electromagnetism, is that an electric or magnetic field strong enough can polarize the vacuum of empty space. Space itself, which is not truly empty but seething with virtual particles constantly flickering in and out of existence, gets distorted by the field. Light traveling near a magnetar does not behave the way light normally behaves. It splits into modes. It slows down. The vacuum becomes, in a very real physical sense, birefringent, meaning it bends different polarizations of light differently, the way a crystal does. This effect, called vacuum birefringence, was predicted theoretically for decades, but was considered essentially impossible to measure, because no magnetic field strong enough to produce a detectable signal exists in any laboratory. Then in 2016, a team using the Very Large Telescope in Chile detected precisely this effect in X-ray light coming from a magnetar called RX J156.53754. The vacuum around a neutron star was visibly, measurably warping the behavior of light. A prediction of quantum physics that had sat untested for 80 years was confirmed, not in a laboratory, but by pointing a telescope at a dead star on the other side of the galaxy. But the magnetic field alone, as staggering as it is, does not fully explain what makes magnetars so violently, almost personally dangerous. The December 2004 event came from a magnetar called SGR 1806-20, and it was triggered by something called a starquake. As a magnetar's magnetic field evolves over time, it exerts stresses on the neutron star's incredibly rigid crust. That crust is the densest solid material that can exist. It is not rock. It is a crystalline lattice of atomic nuclei at densities approaching nuclear matter, with a tensile strength roughly 10 billion times greater than steel. Nothing in the universe is harder, and yet the magnetic field warps and shifts it. Stress builds over years, decades, centuries, and then suddenly, catastrophically, a section of the crust fractures. It does not move far. The displacement in a major starquake might be as small as a centimeter. 1 centimeter of movement in the crust of a neutron star releases, in under a second, energy equivalent to years of the sun's total output. The gamma radiation unleashed propagates outward at the speed of light. And if anything is in the way, there is nothing to be done. The 2004 event was the largest starquake ever recorded. The energy released in that 0.2-second burst was so enormous that some researchers initially wondered whether their instruments were malfunctioning. It was 10,000 times more powerful than any previous soft gamma repeater flare ever detected. It disrupted satellite communications. It affected the ionosphere measurably, logging a signal comparable to a moderate solar flare. And SGR 1806-20 is 50,000 light-years away. The energy that impacted Earth was a vanishingly tiny fraction of the total released. The beam was not even aimed at us. We were simply in the neighborhood. Had this event occurred within roughly 10 light-years of Earth, the gamma radiation would have been sufficient to cause a mass extinction event. Within 3,000 light-years, the effects on the atmosphere would have been catastrophic on a global scale. The nearest known magnetar is about 9,000 light-years away. That margin is comfortable, for now. But there are likely magnetars we have not yet detected, and cataloging them all, understanding their distribution through the galaxy, is not a purely academic exercise. What makes this even more unsettling is how recently magnetars went off in our own galactic backyard in the context of astrophysics. In April 2020, a magnetar inside the Milky Way called SGR 1935+2144 produced something that had never been observed before from a known magnetar. It emitted a burst of radio waves simultaneously with an X-ray flare. A fast radio burst from a confirmed magnetar source, observed in real time in our own galaxy. For years, fast radio bursts, those intense, millisecond duration blasts of radio waves detected arriving from distant galaxies, had been one of the great mysteries of modern astrophysics. Their origin was debated intensely. Dozens of explanations were proposed. The 2020 detection did not close the case entirely, because the observed burst was weaker than extragalactic fast radio bursts by a factor of thousands, suggesting that if magnetars are the source, only the most extreme magnetar events produce what we detect from other galaxies. But it cracked the mystery open in a way nothing else had. The most baffling phenomenon in radio astronomy, these inexplicable screams of radio energy from across the universe, may be the death rattles of magnetar crusts shattering across billions of light-years. The universe has been sending us signals from these catastrophes for decades, and we are only now beginning to read them. There are roughly 30 confirmed magnetars in the Milky Way. Given the size of the galaxy and the observational limitations of our current instruments, estimates suggest the true population is in the thousands. Each one is a compressed stellar remnant wound, to an almost incomprehensible tension by magnetic fields that warp the vacuum of space, crack materials stronger than anything else in existence, and release energy in fractions of a second that dwarf entire stellar lifetimes. They are small enough to fit inside a city. They are old enough to have been there before our species existed. And they are active, restless, and fundamentally unpredictable. The universe does not need to be large to be lethal. Sometimes the most dangerous thing in existence is the smallest object in the room. And that's it from this video. See you in the next one.